Yes. So in photochemistry, we discussed about photochemistry of carbonyl compound. Later we discussed photochemistry of simple olefin. Then photochemistry of diene. There we also discussed about how to use singlet and triplet interaction with 1,3 butadiene. Okay, singlet products are differ over triplet product. Then we also learn 1,4 diene photochemistry, that is dipy-methane rearrangement. Then we also learn oxo-dipy-methane rearrangement, etc. So complete applications are over regarding oxo-dipy-methane rearrangement. Next, photochemistry of benzene. Photochemistry of benzene. Benzene photochemistry. See, benzene is stable in thermal condition. Benzene is stable in thermal condition and unstable in photochemical condition. If I use any photochemical condition, benzene is found to be unstable. It is also called labile. Labile nothing but unstable. You know, inert and labile species in complex compounds it will come. Labile nothing but unstable. Benzene is unstable under photochemically, but thermally it is stable. Thermally we can't participate any benzene. Benzene chemical reactions are very less in case of thermal. Okay, but photochemically benzene is found to be unstable. So that's why photochemically you can participate benzene chemical reactions, but not thermally. Thermally it is found to be highly stable. So you need to remember this point. Photochemically you can participate benzene chemical reactions. Thermally benzene never involved in reactions because they lose their aromaticity. Okay, right. Especially benzene, if they involve in photochemical reactions, they produce complex cyclic strain products. Complex cyclic strain products are obtained by benzene. Benzene produce complex cyclic strain products if they involve in reaction. Then what about reaction exit state? Reaction exit state, pi to pi star, singlet, and rarely pi to pi star triplet. So always consider singlet only. Very rare cases triplet will participate, but triplet also possible to give in chemical reaction. Reaction exit state is singlet as well as triplet, but triplet is very rare, singlet is most common. And if I take any singlet reaction depends on, depends on irradiate wavelength. It is depends on irradiate wavelength. Means what is the lambda of irradiate wavelength? Based on that reaction depends. So singlet reactions, here two reactions are possible. Benzene can participate in singlet as well as triplet, but singlet reactions are depends on irradiate wavelength because variable singlet energies are required. Suppose see, if I take benzene, here three possible irradiations I am using now. This is S0, S1, S2, S3. So from here to here 254 nanometers has been used. Here wavelength for this 254 nanometers for singlet benzene, and this is same singlet. Here there is a requirement of 204 nanometers. From here to here 180 nanometers. So this is the energy order of benzene singlet states. So three possible states are exist for benzene: 254, 204, and one more is 180. These are the possible singlet states only. But most commonly reactions are expected at S1 state. So which is highly stable state for benzene? So I can write highly stable state. Highly stable state is S1 state. So variable products produced from S1 state only, maximum. Okay, because if you go through S2 and S3, stability decreases. Reaction product is decreases. But S1 state is the most stable state for benzene. From there onwards, you are going to expect products. So highly stable state is S1 state and more number of products from S1 state only. So I can write more number of products in S1 state only. S1 state will produce more number of products. Highly stable state is S1 state. Maximum more number of products are produced from S1 state only. So you try to remember 3 common wavelengths are used for benzene. 254, 204, 180. But in that one most common is 254. If lambda is not mentioned, see 3 lambdas are there. 254, 204, 180. If lambda is not mentioned, try to apply 254. Because 254 is a least amount of energy. Okay, so 254 is the least amount of energy where it will give S1 state. From S1 state, more number of products are expected for benzene. Okay, so especially benzene, they involve following photochemical reactions. Benzene involve following photochemical reactions. First one, photocycloisomerization. So this is also called photoisomerization or photocycloisomerization, both are same. Next, photo rearrangement. Photo rearrangement is possible. Then photocycloaddition. Then photo substitution. Then last one, photocyclization. These are the common benzene reactions. Photocycloisomerization, photo rearrangement, photocycloaddition, photo substitution, finally photocyclation. They are the common reactions of benzene. So which is a common state? S1. Many products of benzene belongs to S1 state only. Okay, because S1 state is the most stable state for benzene. And variable photochemical reactions are known such as photoisomerization, otherwise you can say photocycloisomerization, because this isomerization responsible to give ring. That's why sometimes you will see in textbooks as photoisomerization, otherwise photocycloisomerization, both are same. Okay, then photo rearrangement, photocycloaddition, substitution and cyclation. See, photoisomerization. What is photoisomerization? Photoisomerization of benzene. Photoisomerization. See, when benzene reacts with light at 254 nanometers, there is a formation of, this is called benzoylene, then followed by fulvene. 2 products are expected. At this particular lambda, what is this? Benzoylene. And what is this? Fulvene. These are the 2 products at this wavelength. So at the higher wavelength also your answer is remain same, 180 nanometers of wavelength. So there is a formation of, this is called benzoylene and this is called fulvene, and one more is dibarbenzene. Dibarbenzene. So these are the products expected here. So these are most common major, these are major and this is minor. This is minor, it is additional product at higher lambda. Higher lambda means at 204, 180, this product is additionally possible, but S1 state it is not possible. S1 state dibarbenzene not possible. What is this? Benzoylene. You remember this name. This is benzoylene, a double bond and 2 rings. So mostly maximum cases benzoylene is an intermediate. Benzoylene, fulvene. This is called fulvene and this is called dibarbenzene. Dibarbenzene on 2pi cycloaddition, that will give prismane. So this I will explain later. But dibarbenzene is minor in maximum cases. Okay. So even at 204 it is possible. Even at 180 also dibarbenzene possible. But dibarbenzene percentage is very less. Dibarbenzene formation not possible at 254. At 254 Divar benzene not possible to exhibit. So divar benzene preparation done at 204 and one more is 180. But percentage of field is always less, so that's why I can say it is minor. So I am writing benzene photochemical excited state like this. This is called pi to pi star singlet. Pi to pi star singlet. Then see, 2 electrons are present. 1, 2, 3, 4. Now these 2 electrons I am going to write separately now. So this I am writing separately for your understanding purpose. One more time I am writing. See, here double bond and here 4 electrons I am writing. 1, 2, 3, 4. So at higher energy level there is a cross addition takes place between the 2 radicals. So this radical combine, this radical get combined together. So after combination of these two, so what is your expected answer? Expected answer is a bond between these two and here double bond. So this is also represented in the form of like this. See, you can write a 5-membered, put one carbon outside, join these two, you will get this. So this structure also represents this one, both are same. This is called benzoylene. You remember this structure name, benzoylene. Only products they will ask, only products and their names, benzoylene, fulvene and divar benzene. Divar benzene on 2 pi cycloaddition, that will give prismane. That you will discuss later, but remember how to prepare benzoylene, because if you want to understand rearrangement, preparation of benzoylene is very important. How to prepare benzoylene? Take 2 double bonded electrons after excited state, they will undergo cross addition. Cross addition between 2 electron, cross addition between this, you will get benzoylene. Clear? Now, so I am showing how to prepare benzoylene to corresponding fulvene. See, here this electron is undergo photochemical cleavage. Once if it is photochemically cleaved, now here you will expect radical and double bond. Right? Now here one of the hydrogen atom is present, break this. This hydrogen migrates from here to here. So after migration of this hydrogen, so what you will get? Here one radical and here one more radical. Here this bond is as it is or not? Now this hydrogen in the form of radical migrates from this carbon to here. So this hydrogen migration responsible to give this radical and 2 radicals are left. Now later on I am going to cleave left side. If I cleave left side, here you will get one radical or not? Here see, radical like this. Here double bond is present. Now can I cleave this radical? A double bond formation, this and this double bond formation outside, these 2 double bond. What is this? So this is called fulvene. Fulvene is prepared by using benzoylene. You remember that name, benzoylene. Okay, fulvene can be prepared by using benzoylene. See, this fulvene is aromatic in nature. Always if you transfer electrons like this, see, you can also write this molecule like this. You can migrate these pi electrons over this carbon. When pi electrons are migrated outside, always positive, inside always negative. This is the real structure of a fulvene. Because ring becomes aromatic. How many electrons are delocalizing in ring? 6 pi electrons. 1, 2, 3, 4, 5, 6. That's why ring is aromatic. always this outside pi electron tend to migrate on ring side only. Once if they migrate on ring side carbon, now ring carbon carry 2 extra electrons, 2 2 total 4, 4 plus 2 6. Now ring becomes aromatic in nature. So when fulvene is given in your exam, fulvene is aromatic in nature. And always remember, fulvene exo double bond, this is called exo double bond. Fulvene exo double bond always tend to migrate their pi electrons to ring carbon. See, these electrons are migrating to ring carbon only. They never migrate to outside of ring carbon. Which means, suppose if electrons are going outside, here negative and this is positive, then what about this ring? Ring become anti-aromatic. Ring become unstable. So, these pi electrons never go to outside. Always pi electron goes to inside of the ring carbon. So, that's why you will get this structure. Clear? So, you need to remember name. Some names you need to remember, no other option. Some selective names you need to remember. If name is important, then only I will write that name on below of that particular molecule. If name is not that much important, orally I will say the name. But if I write the name of molecule means 100% that is most important for your exam. Any exam. Either it might be a gate examination or CSR exam or DL net. Okay. So any kind of set examinations or any state and central examinations. Once name if I written, definitely there is a possibility of ask that name. Over. Now see one more. When photochemically this is excited, now once if they reaches to S3 or S2 state, there is a formation of excited product. So on that time these two radicals are get combined together. So if these two radicals are combined together, so here see, I can write these 4 electrons like this, 1, 2, 3, 4. Now this and this join together and see, you may expect a divar benzene. This is divar benzene structure. This electron, this electron, this electron, this electron join together. After S2 or S2, S3 state. Now see, once if they reaches to S2, S1, they will come back to S1. Then from S1 onwards it will come back to T1. So even in T1 also this is possible. Now here see, electron, electron, you will get like this. Here spin inversion followed by cyclation, your answer is divar benzene only. Okay, here what about the spin of this electron? Clockwise, clockwise. So I can say spin, spin inversion. Spin, spin inversion, finally you will get divar benzene. So once if you are getting divar benzene, see, I can write divar benzene structure like this. It is a divar benzene structure. So when divar benzene photochemically involved in reaction, 2 pi cycloaddition is possible. This and this get combined together. Now initially there is a double bond is present here. Now this will connect here, this will connect here. There is a formation of prismane. Prismane produced by 2 pi cycloaddition of which one? Divar benzene. It is one photochemical reaction. Preparation of divar benzene is not easy. Once if you prepare divar benzene, photochemical we can convert them into prismane. Okay, so this is separate reaction. This is possible at triplet state, T1 state possible, S2, S1, S2, S3 state is also possible. But S1 state it is not possible to prepare dibarbenzene. If you want to prepare S1 state, first you convert into ISC. S1 converted to T1, inter-system crossing. In T1 state, dibarbenzene possible to prepare. S2, S3 state possible to prepare. It is same way T1 state possible to prepare. That is photo isomerization. Clear? Next, photo rearrangement. Rearrangement possible under photochemically, benzene photo rearrangement. Rearrangement of benzene. C. Take benzene with a proper substitution, especially ortho. Now photochemically, if you irradiate, then this is responsible to give rearrangement will give meta isomer, ortho to meta. This reactions you need to remember. Photochemical irradiation of any benzene with a proper substitution, ortho substitution goes to meta, ortho carbon goes to meta carbon. If meta is given, meta goes to ortho. That is most common reaction. Suppose if three substitutions are present, methyl, methyl, methyl. Now this is most important. If they given 3 methyl, 1, 2, 4 is the major answer. Suppose your answer is 135, 135 trimethyl benzene. When 135 trimethyl benzene on photochemical irradiation, that will give this, you need to remember, 1, 2, 4, 1, 2, 4 trimethyl benzene. So especially if they given tertiary butyl like this. Now photochemical, if it is irradiated, then what is your answer? First position, second position and fourth position. Okay. Suppose 1, 2 photochemical is given. Remember, if it is a tertiary butyl, 1, 2, 4, 1, 2, 4. Now if photochemical is given, on that time see, your answer is dibarbenzene. Here double bond, and here tertiary butyl, here tertiary butyl, and here one more tertiary butyl, 1 to 4. Okay. After getting 1 to 4, further photochemical if it is given, then it is responsible to give dibarbenzene. Dibarbenzene's structure is very, very important. Okay, so here see it is looks like a V shape. Now this bond is connected. Now it is sp2 carbon in planar, it is also in planar. Now here tertiary butyl should be above the plane and here hydrogen also above the plane. So this molecular structure they may also give in your exam like this. They will give double bond, here tertiary butyl and here also tertiary butyl. Here they need to mention thick line and here also hydrogen should be thick line. This is given in CSR exam. When this molecule photochemically irradiated, okay, don't write this answer. When 1, 2, 3 is given, that will give 1, 2, 4. If it is a tertiary butyl, they never give 1, 3, 5. But if it is a normal 1, 3, 1, 3, 5, on the time this is possible. But once if it is forms two tertiary butyls at ortho position, they definitely give divar benzene structure. Divar benzene is more stable. Over here it should be above, here also it should be above. So now this they may give like this, otherwise they may give like this. Okay, always these 2 points, remember, always these 2 should be above the plane. And one more, don't write 2 tertiary butyls over here. Always bridged carbon adjacent, both having a tertiary butyls. And quite opposite, one more tertiary butyl is required. So I can say 1, 2, so you can start give numbering from here. This is thick line, tertiary butyl. Here 1, 2, 3, 4 like this. 1, 2, 3, 4. 1, 2, 3, 4. If this photochemical irradiated, you will get a divar benzene like this. This structure you need to remember. Bicyclic compound, 2 bridge head carbons should be above the plane. This carbon substitution should be above the plane. It is also thick line, it is also thick line. So normally they will write with a normal line. It is projected above direction like this. Don't write thick line here. You should write normal line which indicates that above, that's why thick line. This question repeated in exam, CSR examinations. This question is repeated. 2 times it is repeated, especially in CSR and GATE. Mostly direct question asking in CSR exam. When 1, 2, 4 is given, remember next photochemical irradiation responsible to give divar benzene. Due to bulkiness, not possible to rearrange to give 135. This is 135. Suppose if this is given, you can prepare this. Suppose this is given photochemical, you can prepare this. But when tertiary butyls are given, 135, 135, tri-tertiary butyl benzene is going to give 1, 2, 4, tri-tertiary butyl benzene. From here it is possible, but when if you go for photochemical irradiation, this never give this one. Already crowding is there. So in order to reduce crowding, they will give divar benzene. So when photochemical is given, forward, backward both are possible. Forward, backward both are possible. Forward possible, backward is not possible. So this is on photochemical irradiation. So then what is your answer? Double bond, and here it is a thick line, and here it is thick line. You can write tertiary butyl here and one more tertiary butyl here. That is the answer. That's why this question asking. From here to here question is asking. Be prepared. Normally this is on photochemical irradiation, you will get this. This is on irradiation, still you will get this one. But this is on irradiation, you will get divar benzene product. So rearrangement reaction, remember, always proceeds through, this reaction always proceeds through benzoylene intermediate. Benzoylene intermediate is required if you want to make any rearrangement. Without benzoylene it is impossible to prepare this product. A rearrangement is not possible without benzoylene intermediate. This point also asked in exam. Always proceeds through, these reactions are proceeds through benzoylene intermediate. So don't forget to write thick line here. This is thick line. In options they will give two thick lines, thick line, dotted line they will give. One of the option they will give thick line, dotted line. Thick line, dotted line not possible. So today some questions I send in your WhatsApp group. See that that question will be there. If it is there, no problem. If it is not there, in pericyclic questions it may be there. If it is not available in that one, you go through in pericyclic, definitely it will be there in pericyclic questions. So some questions I transfer to pericyclic, some questions I given directly in photochemistry. See the mechanism. Here double bond and I am writing two methyls. Here Me and this is Me. Photochemical irradiation. Now I am writing 4 electrons over here like this. It is photochemically activated. Me and this is double bond. So what is the reaction state? Pi to pi star singlet. It is activated. Then these electrons are get connected. So once if it is connected, here bond and bond, double bond, and here methyl and this is methyl, right? Then break these two, break this bond and this bond. So after breaking this bond, what happens? See, here double bond and this is one more. So here there is a bond. So here methyl is present and here also methyl, radical, 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 radical. Can I? After breaking this, then this and this join together, this and this join together. So after joining these two, double bond, here one double bond and here also one double bond and this will be connected here. So here it is Me and here Me. If you give numbering 1, 2, 3, first carbon carry methyl and third carbon also carry methyl. Is it benzene? Yes, it is a benzene. So write down benzene structure 1, 2, 3. So first carbon carry methyl and here third carbon carry methyl. 1, 2 rearranges to 1, 3. 1, where one more bond is present? 2. Next bond is 3. What is this intermediate? Benzoylene. If you want to make any rearrangement, always reaction proceed with benzoylene intermediate. So second one, by taking a trimethyl, I am taking 3 methyls, here methyl, methyl, and here one more methyl. So photochemical irradiation directly I am writing now. So we will expect benzoylene. Here methyl, and here methyl, and here methyl. Can I write like this? First I activate it, then I cross this. So from here to here I written in 2 steps. Right now given directly. Can I? So these 2 electrons will be activated now. These 2 electrons are joined, these 2 electrons are joined. You will get this. This and this up to here it is same. Okay? So later on break this bond. So break this bond, break this bond. So after breaking this, so here this and this a double bond, this and this double bond, and here methyl is present, and here one more methyl is present, and here one more methyl. So what is this? Here 1, 3, 5. 1, 3, 5 trimethyl benzene. Now become 1, 2, 1, 2, 3, 4, 3, 4, 1, 2, 4. So this can I write like this? 1, 2, 3. So first carbon methyl, second carbon methyl, fourth carbon methyl. 1, 2, 4. That is the answer. 1, 3, 5, 2, 1, 2, 4. So what is intermediate? Benzoylene. That's why benzoylene structure is very, very important. Without benzoylene, impossible to prepare a proper structure of 1, 3, 5, 2, 1, 2, 4 trialkyl benzene. So that is photo isomerization and photo rearrangement. Next, photocycloaddition on benzene. Benzene also involved in photocycloaddition with unsaturated double bond or triple bond. Here key point is isomerization rearrangement. First you remember benzoylene. How to prepare benzoylene? If you know, 4 marks will be in your hands. Photochemistry of benzene, photo isomerization, photo rearrangement. Try to prepare benzoylene. After preparing benzoylene, left side, right side bond if you break, you will get corresponding 1,2 positions to 1,3 or 1,3 positions to 1,2. Right. See. Benzene reacts with alkene or alkyne. Alkene or alkyne in light to give 1, 2, 1, 3, 1, 4 products. So 3 products are possible. So this is called ortho, meta, para. Benzene undergo photocycloaddition with alkene, alkyne in light. That will give 1, 2, 1, 3, 1, 4 products are possible. 1, 2 nothing but ortho position, 1, 3 nothing but meta position, 1, 4 is para position coupling. Okay. See, 1, 2 are ortho addition. 1, 2 are ortho addition are highly predominate. One two addition or ortho addition is highly predominate as compared to any. 3 are possible, but major is 1 2 only. Okay. So if I take any alkyne triple bond, alkyne always give ortho addition. Ortho otherwise 1 2 addition only. Triple bond never give meta addition. Triple bond never give para addition. Triple bond always give 1 2 addition only. Alkyne. But what about this one? Alkene. Alkene will give 3 products. In that 1 2 is major. But alkene triple bond. When alkyne is given, on that time only 1 2 is possible. 1 2 addition. Okay, 1 2 addition nothing but ortho addition. Reaction exit state is pi to pi star singlet. Pi to pi star singlet. And if I take any conjugate olefins or conjugate dienes they involve in 1, 4 addition. This is called para addition. Conjugate olefins always give para addition, but remaining all will give ortho addition. Meta is minor. So here I am writing benzene and here a olefin I am taking now. This is photochemically ortho 1, 2. Ortho are 1, 2 addition. You will get this answer directly. This is 1, 2, 3, 4, 5, 6. 1, 2 is ortho. Then what about photochemical? One more product is also possible. What is it? Meta. Meta addition is nothing but 1, 3. 1, 3 means you will get like this. This is called 1, 3 addition. Okay. Then one more product is also possible. Photochemically, para is possible. What is para? 1, 4. 1, 4 addition means you can write like this. Double bond, double bond. This will be connected like this. So when triple bond is reacting with this, then what is your answer? See, when carbon triple bond is given, which is predominate always? Ortho is predominate here. Ortho means you can write like this. So it is an example of 2 pi supra cycloaddition. Finally, what is your answer? There is a double bond formation takes place like this. Right? Triple bond become double bond. And what is the stereochemistry of these two hydrogens? Cis to each other. See, slowly we are entering into pericycle. Now this is undergo ring opening. And even you can go for right side. Then what is your final answer? Final answer is 8-membered ring. This I given see in your notes in pericycle. 8-membered I prepared. Cycloocta tetraene. If this molecule is given, this is prepared by benzene reacting with triple bond. Only possible with triple bond only. Then double bond and here 2 double bonds are present. They undergo ring opening and there is a possibility of preparing cycloocta tetraene. That's why try to learn pericycle photochemistry at a time. All reactions you group at one place. Try to make a short notes. Then try to prepare parallelly. 2 advantages will be there. First advantage, if any mixed question is given with pericyclic and photochemistry, you can attempt. If separate question is given, you can attempt individually. And many reactions with reagents and pericycle, reagents and photochemistry are well known. Up to now we discussed about Pattern-Bush reaction, Norris 1 reaction, Norris 2 reaction, dipymethane, oxidipymethane, etc. They are the standard reaction. Next is going to come, Barton reaction is going to come. From Barton also one question is coming. Barton chemical reaction. If any conjugate partner is given, go for 1,4 addition. Simple olefin is given, go for 1,2 only. 1,2 is predominate under photochemically as compared to 1,4. 1,3 possible, 1,4 possible when I use any double bond. But 1,2 is dominating. Clear? See, mechanism I will give directly 1,2, no problem at all. If I take any double bond over here, now this electron, this electron, this electron, this electron directly join together. Okay? So if they join together, initially you will get 4 electrons. Here this 4 electron, there is a transition state possible here. So after transition state, what is your answer? You will get this product. Right? So this is your first one regarding ortho. Suppose if I take meta, now 4 electrons are going to involve here now. 4 electrons are possible. Now here this and this. Here they are going to interact like this. Here 1, 2, 3, 4. Here 2 electrons are present. Now this 2 will join here, this 2 will join here. So this 2 will join here and this 2 will be joining here. This is called meta addition. Meta addition you will get like this. You can write with benzene structure even, you can also predict. This is double bond and one more, there is a possibility of double bond here. You can also write like this structure. This structure you can also write like this. Okay, then go for para. Para is very easy. So here I am using 4 electrons still. 1, 2, 3, 4. 2 electrons here. So 1, 2, 3, 4. This is joining this electron and this is joining this electron. Okay, so after joining these two electrons are joins together, form double bond, and see here there is a single bond and here single bond, 2 methyl, 2 methyl, that is the answer. See, if I write reaction, you are in a position to guess where interaction is going on. That much standards you need to reach. That will help in research. Your guide will ask that, so this molecule if I participate, I got this answer. Will you write the mechanism? They will ask. You need to write different mechanisms, possible mechanisms. In that one, which is correct, that will be confirmed by spectra. That's why reaction, intermediate, product, spectra. Only these are sufficient for your research. Stereochemistry, that is well known. If you are very strong in stereochemistry, then only you can move next step. First thing is mechanism. By watching the molecule, you are in a position, you need to frame that points in your mind. How electrons are attaching, how it is forming, like that. No need to by head. Don't by head reactions and mechanisms. If you by head, that will remember temporarily. If you want to remember permanent, try to think about reaction. So this kind of reaction, somewhere I given. Where? Yesterday I given. Yesterday I given this one. This I given. Beryllium into semi-bulvalin. See yesterday. Photochemistry of 1,4 diene. Third reaction, see. Where I given heading. Photochemistry of 1,4 diene. Photochemistry of pentadiene. Zimmermann rearrangement. Then I written 3 reactions. Then I given definition. Third reaction, see. Beryllium, this molecule I given, see, is it given or not? From here to where I given? Beryllium into semi-bulvalin, that is bulvalin structure. But here what is the difference between bulvalin and this one? Here 2 double bonds are not there. That is the difference. See, here I am giving benzene. So a normal double bond is given OET, OET. Photochemical, what is the answer? If simple olefin is given, which is predominate? Ortho, meta or para? Ortho. If triple bond is given, blindly go for 1, 2 only. When double bond is given, 3 products are possible, but ortho is major. When triple bond is given, only ortho is major. So what is your answer? Can I write like this? Here I am writing OET and here also OET. So now this is not found to be stable. Now this will undergo ring opening. Once if they undergo ring opening, how many double bonds you will write? Write the answer for that. After getting this, don't stop reaction here. You further open ring. How many double bonds? 3. So 1, 1, 1. This is OET, OET. This is on acid hydrolysis. So simply go for hydrolysis here. Then diol formation takes place. Here OH and here also OH. This is on further dehydration. 1 carbon 2 hydroxy. There is a loss of water molecule. Finally, you will get this one. This is given in exam. First they will give photochemical, you will get this one. Go for ring opening, you will get this. This is on acid hydrolysis, you will get this. So this two, they will ask A. A is this one, not this. Intermediate is this. Later on undergo ring opening, you will get this. Then this is your B when acid medium is given. Now 2 pi cycloaddition. So this is double bond COOET, COOET. Open this side and migrate here. So how many member ring? 8 member ring, and here COOET and here also COOET. That is the answer. It is important for pericycle even. A double bond, photochemical, give the answer. Same. This and this you combine together, give the answer. You take down this as homework. This you take down as homework. Similar reactions, all are 1 2. This is 1 4. Is it conjugate diene or not? 1 2 3 4, 1 comma 4 addition, 1 comma 4 addition reaction. Here what is the stereochemistry of these two? Here hydrogen is present, here hydrogen is present. Superficial, it is superficial means here I can write thick line. That is the advantage of pericycle in photochemistry. Two you need to know, photochemistry and pericycle. So take down these questions, you work out later. Here 2 pi cycloaddition takes place between excited benzene and ground state benzene. Both are possible. So this will combine with this and forms 4-membered ring. Next, photo substitution reaction. Photo substitution reactions are generally classified into two types. First one, photoelectrophilic substitution. Second one, photonucleophilic substitution. Directly I will write. Photoelectrophilic substitution. So remember, they are highly inert. These reactions are not known. They are highly inert due to electrophile acts as quencher. So in this particular reaction, electrophile is acts as a quencher. That's why EPS, photo EPS is not possible. This is called photo EPS, EPS, electrophilic substitution, which means if I want to add any electrophile photochemically, okay, reaction is not exist, no reaction. We can't add any electrophile on benzene under photochemically because it is at photochemical state, excited, it is a quencher. So it will combine with this and make them into ground state. So when benzene comes at ground state, there is no photochemical reaction. So now this is acts as a, how it is acting? It is acts as a quencher. That's why photo EPS is not known. This electrophile is acts as a quencher. It is ground state, it is at S1 state after photochemical irradiation. So this and this get combined together, it will make this at ground state. So that's why photo UPS is not known. No alkylation, no acylation, no Friedel-Crafts alkylation, no Friedel-Crafts acylation, nitration, halogenation, sulfonation, EPS reactions are not known. Clear? Be prepared. Substitution reactions are two types. You can add a electrophile, we can add a nucleophile. If you add a electrophile, photo-electrophilic substitution. If you add a nucleophile, photo-nucleophilic substitution. Adding electrophile on benzene under photochemically not possible. Thermally possible. That is normal. Friedel-Crafts alkylation, Friedel-Crafts acylation, nitration, halogenation, sulfonation, this all are belongs to this reactions only. But photochemically, we can't add any electrophile on benzene because benzene is at excited state. This electrophile acts as a quencher. Take this. Photonucleophilic substitution. This is possible. Now we are adding a nucleophile on benzene. Adding nucleophile on benzene possible, but adding electrophile on benzene not possible under photochemically. So that's why in your textbooks, if you see photo substitution, they will explain directly photonucleophilic substitution. They won't mention the word photoelectrophilic substitution. They won't use this word because they know very well this is excited, it is a quencher. Once if they forms a exiplex, on the time this will becomes a ground state. The ground state reactions are not photochemical reactions. That is the drawback. That's why adding electrophile on benzene under photochemically not exist. They are highly inert due to electrophile acts as quencher. See, suppose if I take benzene, photochemically I can introduce any nucleophile. If nucleophile is given, that nucleophile will be added on benzene directly. Like this. Directly we can add a nucleophile on benzene. It is possible. Thermal reaction products are quite opposite to photochemical reaction product. Thermal products and photochemical products are not same. Thermal reaction products are quite opposite to photochemical products. So thermally, see, if any electron withdrawing group is given, thermally electron withdrawing group is present on benzene. Okay, so on that time it will be ortho para director. Para is predominant over ortho. Para predominant over ortho. Thermally, when any electron withdrawing group present on benzene. Now benzene, what is the substitution present? No substitution. But right now what is the substitution? It is electron withdrawing group. When benzene carry electron withdrawing group, under thermally, okay, one more whatever electron withdrawing group you are adding, on that time it is a ortho para director. Okay, so if I use any electron releasing group, donor, then it is a meta director. Now this reaction is quite opposite under photochemical. When photochemical is given, it is quite opposite. When electron withdrawing group is given, it is a meta director. When electron releasing group is given, ortho para director, it is quite common, para is predominant over ortho. You remember these points. It is normal study. Normal study means, so in your EPS reactions and in your normal thermal ground state reactions, that will be like this. If benzene carry any electron withdrawing group, under normal thermal condition, it can withdraw electrons from ortho and para. So ortho para carry less electron density because it is taking that electron density. Then incoming nucleophile will be, this nucleophile is going to be added it, either ortho or para. So between ortho and para is predominant over ortho. Suppose if any donating group is present on benzene, it is a meta director. Okay? When benzene carry any electron withdrawing group, what type of group is present here? What type of group present on this benzene? Any group is there? No group. Okay? Here no problem at all. This kind of molecule, no problem. Suppose if this molecule I want to participate in photochemically or thermally, on that time you need to see what is the nature of that substitution, whether it is a deactivating group or activating group. Suppose if it is a deactivating group, withdrawing groups allow nucleophile at which position? Ortho para. Donating groups allow meta. Photochemically opposite. Photochemically electron withdrawing group meta director, donating groups are ortho para director. Clear? Right. So this you need to focus right now. See, I am using a nitrobenzene. What is the role of nitro on benzene? So thermally I want to add a cyanide ion. Potassium cyanide, sodium cyanide they will give. I want to add cyanide ion. Photochemically also I want to add cyanide ion. What is the role of nitro? Nitro is a electron withdrawing group. Normal I am explaining. Nitro is electron withdrawing group that can decrease electron density at which positions? Ortho and para positions normally, not photochemically. Thermally or room temperature. Normal character of a benzene. Okay? If any withdrawing group present on benzene, that group can withdraw electrons from which position? Ortho and para. Okay? Suppose if I take any releasing group, So what is the nature of methoxy? Methoxy is a releasing group. It can release electron. Mesomeric effect group. Now what happens? See, thermally I am adding cyanide ion. Photochemically I am adding cyanide ion. Now see the concept. When this is a normal study, I am not using thermal photochemical. I am explaining the property of this molecule in normal cases, means in ground state, room temperature. When Widran group is present, that can decrease electron density at ortho and para, and it won't affect meta. Meta it cannot take electron. So out of ortho para, where electron density is more affected, para. This can take more electrons from para, then followed by ortho, then meta. Now when methoxy group is given, it can release electrons at ortho and para. Ortho carry more electrons, para also carry more electrons as compared to meta. If any releasing group is there, that will give electrons to ortho para. If any withdrawing group is there, that can take electron from ortho para. Who is neutral? Meta. Meta position is unaffected. Now the concept is, under thermally we can apply like this directly. Thermally I want to attack cyanide ion. Cyanide ion is a nucleophile. It will attack on that particular benzene carbon where electron density is very less. Where it will attack? Ortho para. Out of ortho para, which is predominate? Electron withdrawing group. Para predominate over ortho. So can I write cyno on para position? Here nitro is as it is, here cyno. Then what about photochemical? Quite opposite. So quite opposite means we need to write it meta position. Electron withdrawing group is what? Meta director. So don't write ortho. Here we are writing para means you will say, sir, here I want to write para or ortho. Wrong. Quite opposite. Now see, it is releasing electron where electron density is very high, ortho and para. Out of ortho para, which will carry more electron density? Para carry more electron density as compared to ortho. Ortho carry more electron density as compared to meta. Right? So out of these three positions, where electron density is less? Where electron density is less? Meta. So what is coming? Nucleophile is coming or electrophile is coming? Nucleophile. Nucleophile attacks on that particular benzene carbon where electron density is less. Where it will attack? It will attack on which position? Where it will attack? Say the answer. Are you able to understand or simply you are sitting in class? If you are unable to understand, stand and listen the concept, then you will understand clearly. Because you are sitting now, so comfortable will be there. Relaxed. Mind will be stable. Once if you stand and write, then see, body will be not supportive. Body is getting strained. On that time, mind is active. That's why in olden days they are giving punishment for that reason only. Actually you are active only, but due to comfortable, your mind is inactive. So I want to make your mind active. How should I make? By giving punishment. Only one option. Punishment is the best alternative for activating your mind. Right or not? See, one day before you try to read any concept. Tomorrow morning exam is there. Open today night. Morning 10 o'clock exam is there. Open today night at 9 o'clock. Then see how that concept will enter in your mind. Within seconds, you don't believe your capacity of your mind. Only one time that will be printed in your mind. And even the topic not understood for 6 months. Throughout semester, you won't understood. You are written many internal exams. Many examinations you written. But the topic is not understood clearly. Simply you are beheading and you are writing. But on the time, read one day before the topic. See the capacity of your mind. That is called Einstein mind. Einstein mind works like that. Okay? So you can, but due to negligency, that won't be entered. So be active every time. So that's why on that times they are giving punishments for this reason only. Because your body is, when body is stable, your mind will not work. You try to check out. Suppose on main road, whenever if you are crossing a road very carelessly, if suddenly one bike person, those who are riding a bike, he came suddenly, they stop in front of you. Main road, suddenly he was stopped. Then see, which will be activated? Your sleeping mode, everything will be disappears out. Why? Punishment. You are experiencing punishment. Your bodies get activated. So that's why there is no inactiveness. Inactiveness created by yourself only. Activeness created by other persons. So if you want to get activeness, try to fight with your friend. Okay? So give a slap, then automatically your laziness will be disappears out. So you can read continuously. So these points are very, very helpful for your basic property of any benzene substitution. When benzene substitution carry donor or withdrawing group, that is normal thermal condition. Photochemical they will mention directly. Suppose if it is any electron withdrawing group, it can decrease electron density at ortho para. It can decrease more electron density para as compared to ortho. Para having more reactivity as compared to ortho, then followed by meta. I am saying that it can take electrons more from para. So para having less electron density or not? That's why cyano attacks on para. Now this group is releasing electron. This is an electron releasing group on benzene. It can release electrons more on which place? Ortho and para, not on meta. Out of ortho para, where it will release more electrons? Para. Para having more electrons as compared to ortho, then followed by meta. But what we are attacking? Cyanide ion, negative ion, nucleophile. Nucleophile attacks always at that particular carbon where electron density less. So out of these three, where electron density less? Meta. So that's why I am attacking it meta. Cyanide, vinide, meta. So thermally, electron withdrawing groups, ortho, this one. But when electron releasing group is there, meta director. Thermally, meta director. But if you go through this one, it is quite opposite or not? So where you will add? You will add it para position, quite opposite. Photochemical reactions are quite opposite to thermal. So that is photonucleophilic substitution. So this is last one.